This part of the video is not really necessary, so if you wish you can skip this part, but if you are algebra oriented person, if you like algebra, this could be really fun. It's pushing ourselves more to this operator algebra, which is not absolutely necessary to deal with the problem, especially getting the solution and solving the problems. This part's not necessary, but since it's titled operator algebra, we've shown a little bit already, but this could be fun. Here's a very simple motivational question. This is the equation 2x equals 5, and x is supposed to be a number. And I'd like to look at this left-hand side as an operation on numbers. So operation on numbers is called a function. It's a 2 times function. If given a number, we multiply 2. That's an instruction or algorithm. And often we learn how to solve this problem. In algebraic point of view or a functorial point of view, you can describe the entire solving process as follows. What we're really doing when we solve is that doing operations to both sides of the equation. If you put all this operation we're doing to the left-hand side and right-hand side all together, that whole sequence of operator can be called a single operator, and relative to what it's doing to this 2 times a function is called inverse operator. So if you do this operator, sequence of operators, call it inverse operator relative to its 2 times, it kind of annihilates this function. So it is doing 2 times a function, this inverses reverses it, so it cancels this operation, and eventually at the end up at doing nothing to the input. Here's 2 times a function. This is what it's doing to the given input. Inverses annihilates, so end up at doing nothing to the input. So input is x, together with this one and 2 times becomes just x. And this is what we learned on early hour education. This 2 times x equals 5. If you do this inverse operator, 1/2 and 1/2 both sides, what happens to the left-hand side is that it just have x in it. X is the original input. After you go through these 2 operator, it cancel each other. It does nothing to the input. So we happen to have isolated x on the left-hand side and right-hand side. It's whatever it is. So that tells you x equals 5/2. This existence of this inverse operator always implies that this is the only solution, only candidate. Often that part of the logic is not emphasized because the kids can't handle that much of a rigor or logical part. But you're not, so think about it. This really, if there is a number x, and we can do this inverse operator, and you end up with this number. Sometimes there is no single operator. For example, if x squared equals 5, we think about inverse operator, and you end up at a little bit of trouble to find an inverse operator if this is the case, x squared equals 5. So this is a very simple example, but that's what we're going to be doing algebraically to our differential equation. So I'm going to look at this first order linear differential equation, y prime plus qx function in x, and y, a known function, rx is also a known function. So this is where we started. Now we have a fancy version of this one. Is an operator, d plus qxi, as a single operator with this name, operating on this unknown function, y becomes rx. So what I was saying is that if I can find an operator that annihilates this one, so-called inverse operator, then maybe y is going to be isolated here, and right-hand side is going to be the answer. So we have to find out if d plus qxi is one operator, what could be the inverse operator, so that these 2 operators cancel each other, leaving y in the left-hand side. And if you do the same operator on the right-hand side, and you end up as solving this equation. Remember that in this equation, without initial condition, had infinitely many solutions. So we don't expect that there's one single operator that annihilates and give you the answer. It seems like there's only one answer if that's going to happen. So you will encounter some sort of choices involved in this operator, but it's not too bad. So I'm introducing here. Of course, the way we solve this equation in pretty much in standard form, I should call this as an operator form. This left-hand side is an operator acting on the function y, and then y, and right-hand side is rx. But it is this integrating factor. If you multiply this integrating factor everywhere, left-hand side becomes integrable as an elementary function, or some nice antiderivative shows up. That's one way to say it. So let's review that. So in terms of operator algebra, it goes like this. I hit it. After you multiply, the left-hand side becomes derivative of something, it coming out of product rule. So I actually started from the product rule. If I have a function, which is represented by identity operator here, multiplied by this specific function, the q, capital Q, is antiderivative of little q. So if I have this operator, if you were still wanted to think of this as functions, is that eq, the function in x, and I is some input function or unknown function y. And this is differentiating these two functions. And of course, the product rule says this has to be differentiated. So that looks like this, q, little q times eq. And this has to be differentiated, so this d is acting on that part. So product rule says this one, so we've already seen that. Sorry, it shook a little bit. So you can reorganize this like this, eq, common factor, to factor out. We usually write d first, and d is coming as a first term, and q plus I. So this integrating factor as an operator algebra can be rearranged like this. If you have d plus qi, and if you multiply this operator by this function eq, this is equivalent to d of eqi, basically the product rule reversed. Okay, so that's the operator algebra version of this integrating factor phenomenon. So I wrote it down here. What we really need is backward. If you see d plus qi, you can multiply that by this one eq, and then this becomes rearranged like this nicely. So if d is over here, if you hit it with the integral, you know this d and integral cancels, and that's the whole idea of the motivation to rearranging this algebra, operator algebra in this way. So let me explain the rest of the part in an operator algebraic terms. So we have d plus qi, that's what we had before, and we multiply eq, which is q here, it's the antiderivative of little q, then we arrive at here, this identically equal. Then we're going to hit it with the operator, integral operator, so that I can get rid of this d, and that's the whole trick here. We want to get rid of this d. So let's hit it with the integral operator here. So here it is. If I hit it with the integral operator on here, and this d and this one, that cancel. If d is outside of the integral first, then it is just simply identity, but here it is inside, we have a little bit of factor showing up. So since these two cancel, it leaves identity, which is inside here, so that should be copied here, eqi, and evaluation on that part, evaluation at a. This is an operator. Think about it, this is a function, eq and y, and evaluated here, that will be eqa and y of a. So that's the same. You know this part is going to be just a multiplicative constant evaluated at a, so we can rewrite this one as follows. Like this one, here's eqi, this identity, and this is just a constant function evaluated at a times this particular factor. So now here's a summary. So finally, if you multiply e to the negative q both sides to the operator equation, then you arrive at here. E to the q was here before, but as you multiply e to the negative q, we arrive at here. So we start from here, d plus qxi. If you multiply eq and integrate and multiply by the e to the negative q, if you go through this operator, what happened to this entire operator is identity. This is nice. Identity is what we wanted, to isolate this entire kind of annihilates the entire operator. But there is this additional term. This is not too bad if you look at it here. So that part was mistakes, so I got rid of it. So this is the summary from what we have calculated there. Identity minus this vector with the evaluation operator. So this is a really nice way to isolate this operator or annihilate this operator d plus qxi. So let's use this idea to see what we can do about second order equation. As usual, I've forgotten what's prepared underneath it, so we're going to actually look at this particular example and see this inverse operator in action and with this actual example. So this is first order linear differential equation. An operator term is described like this, d plus 2i y, and this doesn't have to be a constant in this case, it could be a function in x. Sorry, it moved around a little bit, but here's the copy of the corollary again. If you're looking at d plus qxi as an operator, if you go through this operator, it annihilates pretty much, leaving you this I part and evaluating in it here. So this is a pretty good annihilation. Not perfect, but it's pretty good. So that's what we're going to do. D plus 2i. Here's q, little q is 2, so that big Q is going to be 2x. So that's what I'm doing for both sides. The d plus 2i, we have this 3 operator multiplied by 2e to the 2x, integral operator, multiplied by e to the negative 2x. That the same operator is done on the left hand side. So I forgot to do this e to the 2t multiplied to the right hand side, so I did it. So that's the part. This is just no, you can integrate it, integration by parts, and you can actually calculate this one explicitly. What happens left hand side with these 3 operators done to this d plus 2i is because the corollary, it becomes this I minus e to the negative qx times e to the qa evaluated and the evaluation operator ea. So that's whole thing, it's operating on function y. Right hand side is this actual function. Now if you change that to more functional notation, then this is going to be y, nicely isolated here. This is what we wanted to solve for. Y minus, this part is abbreviated here, and y of a shows up. So this solution depends on what your initial value here is. So that's kind of the operational summary of our integrating factor technique on the first order equation.